physics. So here, what you see is cross-section as a function of the photon-proton center of mass energy. These are for measurements in EP collisions, and it's for different vector measures that have been produced. So for the rho, for the omega, which is a bit heavier than the rho, for the phi, which is a bit heavier than the omega, then for the j psi, which is quite heavier, and psi 2s, which is a resonance state of the j psi, and the epsilon quark volume, which is even heavier. And this is for quasi-real photons, so virtuality close to 0. And what you see is that for the lightest vector mesons, this is quite flat, but then the heavier and heavier the vector mesons, and there's the quarks constituting the vector meson, the more you see stronger dependence as a function of W of this cross-section. So what is beautiful of this picture is that you really see the transition from soft physics, which is rho, omega, and also phi, to perturbative QCD, which is starting from production of j psi and epsilon. So this is just beautiful to visually see this. You actually can play the same game, but then with producing, for example, a rho. But now you first start with photon production of a rho, so with using a photon that has virtuality close to 0. And then if you increase the virtuality of your photon, you start to again see a steeper slope as a function of W. So this just that you visually see this transition from soft to hard. Because I also say this, there are people measuring photo production of rho, but there you don't have this hard scale, so it's much more complicated to interpret. And this picture really shows you this beautiful transition that and proving that these are really different regimes. Another plot that I like to show you is the cross-section differential in this momentum transfer T as a function of T for, again, rho production for different values of Q squared. And the idea is that if you look at the dependence as a function of T of your cross-section, you can fit it with an exponential, and the constant that you obtain from your fit called B actually gives you a measure for the transverse size of the object involved in your interaction. So in this case here, we have our photon fitting into a gigantic quark and then forming a gluon. So here we have a dipole, and your dipole can have a certain size, and you have your proton, which also has a certain size. So this B parameter is sensitive and to the size of your dipole and to the size of your G. Now, if you look at this B parameter as a function of the hard scale, where the hard scale can be in part due to the high virtuality of your incoming photon, or also the mass of your fine meson, so such as for the j psi and the epsilon. But you see that in the non-perturbative regime, so close to 0, you have a very large value of B. And then even if you're already in the perturbative regime, you see you're still quite high, and you see that actually the higher your perturbative scale, the more this goes down, up to at some point reaching a constant value. And what this actually means is that you have here your dipole that has a certain size, you have your proton that has a certain size. These are both encoded into this B factor, but then higher and higher Q square means your dipole becomes smaller and smaller and smaller and smaller, up to a point where it has no influence anymore, and you're only sensitive to the size of the proton, size of the object that you're probing. Here with high energy, so we're actually probing the gluon inside your nucleon. So this actually gives you a measure for the radius coming from your gluons, which is estimated to be 0.6 Fermi. Okay, so this type of games you can play in exclusive physics. They're not directly related to GPD, only indirectly, but I think these are nice pictures if you enter this world of exclusive physics for the first time. So now going formally to the GPDs. So we can study, for example, exclusive or phi or omega, and we have seen this diagram already several times, but we can look at the same process in a bit a different way. So I have the virtual photon, here a blob, and you produce your vector meson, and here you have the nucleon, and these two here are particles, they can interchange particles of different types. So we can have a natural parity exchange, so depending on the total angular momentum and the parity, and then you are sensitive to the GPDs H, E, and some combination of H tilde transversity and E transversity or ET, and then you can also have the exchange of unnatural parity, and then you access H tilde and E tilde, for example. Now, the reason I say this so explicitly is because when we want to describe actually our transition from a virtual photon with a certain helicity interacting with a nucleon with a certain helicity to final state, which is a vector meson with a certain helicity, and your recoil nucleon, again in a certain helicity state. So this transition is described by so-called helicity amplitudes. Please bear with me. It's not an easy, it's quite complicated. So we have this helicity amplitude, and these helicity amplitudes have one part that corresponds to the natural parity exchange, sensitive to these GPDs, and one part that corresponds to the unnatural parity exchange. Now, what we access in experiments is two different things. What we can do, we can access so-called helicity amplitude ratios, which are just ratios of either the natural parity or the unnatural parity component of your helicity amplitude compared to or divided by some dominant amplitude component. So you just always divide by this. So you access this ratio when you perform your experiment, or you can also construct what are called spin density matrix elements, which are where again your helicity amplitudes enter. It's more complicated, but the thing is, when you perform your measurements, you can either access this or these are the things that we will access. These things are related to your helicity amplitude. And now these helicity amplitudes are related to your GPDs. And here I show how they are related using one model. And here you have the helicity amplitude where your nucleon doesn't change. And you see this can be written as, again, a convolution of some hard scattering, the hard scattering part, and your GPD H and E, and also H tilde and E tilde. So this is, again, your natural parity selection, and this is your unnatural parity. And the same if your nucleon flips its spin. So this is how the theoreticians do it in their model. So they determine actually your helicity amplitudes, and then the experimentalists, we access these helicity amplitudes by looking at ratios or SDMs. So that's the principle. Is that more or less clear, the idea behind it? Yes or no? I have to stop?
No, is it a good place to stop?
No. But you prefer me to stop? I stop. Okay, give me that 1 second. So is this clear for the principle behind? Yes? Okay, more or less. Yes, I know it's complicated. So, but if you get the idea, that's the important. Okay, and now the way that we access this is in principle quite simple. So you look at your exclusive row production, for example, and you reconstruct all possible angles you can think of. So you can have the angle between the plane formed by your incoming, outgoing lepton and the plane formed by your virtual photon and your outgoing nucleon. You have the plane between the second plane I discussed and the decay plane of your hole, etc. Okay, so all possible angles you can think of, extract, and then you perform a fit of your distribution to all of these angles. And the parameters of these fits are either this or this. Okay, you just make a fit of your angular distribution of all possible angles, and then you actually provide this to the theorists, then you can go to bed or whatever. And these theories then from this extract information of the GPDs. Okay, so that's the idea. Or better said, they have a model for the GPD. They determine these coefficients, and then we compare the coefficients with them. So here you see one example of all these different coefficients that have been determined. This is for using an unpolarized target and a longitudinally polarized electron beam. And you see there are really many elements that you can determine, and they're sensitive to different GPDs. For example, these ones here, which are clearly non-zero, are sensitive to GPD-H, which we can also access in DBCS. But then what is nice here is that you have also coefficients which correspond to the transition of a transversely polarized photon to a transversely polarized photon goes into a longitudinally polarized vector meson. So you have a change of helicity from one state to the other. Whereas here, you don't. You go from longitudinal to longitudinal or from transverse to transverse polarization. So these are the most easy ones, but you also have non-zero values where you have a change in polarization. And these, for example, are sensitive to the transversity GPD. These are not easily accessible in DBCS. Okay, so this is just one example of how vector meson production helps us more. And then I've just one more slide, and then I will stop for a second. So there have also been similar measurements, but then at the HERA collider experiments, where they were able to also study heavier vector mesons such as the JLab. And there, however, they don't see any contribution from events where you have a helicity, a change in helicity state or polarization state from your virtual photon, your final state JPSI. So for these heavy JPSI particles, there's no change in. And I'm gonna, okay, while they set up, I continue. So there are also a series, as already mentioned, of upcoming experiments where they will probe GPD. But at Jefferson Lab, there are new experiments like ALERT and also experiments studying ion production, which is very useful. And then the idea is to, in 5 or 6 years, to also have experiments where you can probe double DBCS. So you start with an incoming virtual photon and you end with and you have an outgoing virtual photon. So twice virtual. And the huge advantage of this is that you then finally can probe for GPDs for different points in X and Xi. The drawback is that this cross section is very reduced. So let's see what it is. And then, of course, we also will have measurements for the EIC. And as I mentioned yesterday also, so at the EIC, there is this far forward system where you can actually detect the scattered photon, if it didn't break up, using the detectors here or the Raman pots. And here you see an example of, in blue, of distribution of generated photons in exclusive production. And this is then how well we can detect them in this far forward system, which is actually really nice and quite good. So this gives us a cleaner measurement than if you do not detect your final state photon. And this is, well, just some plot to show you how many events we expect for a certain being in X and Q squared as a function of T at the IC. So this is really good statistics. So this will really nice. And this will help us to constrain our Compton form factors a lot. So this is H, the Compton form factor H in green as we know it nowadays, which is the best well known. But still with DIC, we will be able to constrain it a lot more. And then this is an example for the Compton form factor. Be careful. So Compton form factor is not yet your GPD, right? You still need to extract it from your convolution. So it's a bit more complicated. And I'm gonna stop. I'm gonna stop here now. Well, I will continue. Sorry, thank you. She just has to make an announcement.
I am. I need to do a PowerPoint. Because it's a little bit of a briefing. Let's give it a shot. Okay. Right, I wanted to come in and chat with you guys about the your final reception that's gonna be on Thursday. It also is coinciding with what we call an S4 visit. It's the undersecretary for the from the federal government, from Department of Energy, will be here to see the facility, participate in the groundbreaking, and get to see you all in all of your glory and all the stuff that you've been doing for the past.
Okay, so let's continue because we have less time than foreseen.
I don't have any shirts.
So I've mentioned that, and I've shown result on exclusive JLab production with an incoming real photon, where this photon comes from the electron beam, but we can actually also obtain a real or quasi-real photon from a hadron beam. So we can look at exclusive production in hadron-hadron collisions, such as at RIC and at the LHC. And then, so here you have one of your beam hadrons that serves as a photon emitter, and you use then that photon to probe your other beam hadron. But again, what is really important if you want to be in the conservative regime is that you have a hard scale, so you can only look at particles consisting of heavy quarks. There are also studies ongoing where they look at photo production of Rho, but that's then another domain, and you cannot extract information about GPDs there because you cannot do from your factorization, and you actually don't really. Now, I said this has been done at Hadron Collider, so at RIC, at the Tevatron, at Fermilab, and at the LHC. And the huge advantage of looking at this process in hadron-hadron colliders, especially at the LHC, with its huge energy, is that you can go down to X-Bjorken of 10 to the -6. So in EP, you go down to 10 to the -4 if you have a collider. And here at the LHC, we can go down to X values that are otherwise not accessible. So this is really nice. It's more complicated. It's not as clean. Again, you don't know the end of the school. You don't know the energy of the precise kinematics of the photon. You have to make some approximations, but okay, on average, anyway, it's really nice. Okay, so you have again kinematic variables that you need to reconstruct. So your hard scale, as already mentioned, is given by the mass of your final state particle. So it's a fixed scale though, depending on the particle that you're solving. And then you can reconstruct the X-Bjorken variable as we saw for the dijet and the W production in PP, just based on the information of the mass of your final state particle, the center of mass energy of the collision, and especially then the rapidity, so the direction in which your particle is collision. So I already mentioned this, but so this is the kinematic approach. This is if you use your J psi, you have a fixed Q square determined by the mass of your charm quark. So this is where you reach if you look at proton lead and lead collisions, and if you look at proton collisions, you can really go down to 10 to the minus 6. The epsilon gives you information at a bit higher scale and a bit larger values in X-Bjorken, but you can also go down to 10 to the minus 5. So this is extremely nice about them. And this is what we would probe with the EIC, of course, a continuous regime and not at the fixed scale, very precise. Now, how do we perform these measurements at the LHC? Well, or at RIC, we look at ultra-peripheral collisions. So we look at collisions of beam particles that are far away one from another. In practice, it means that their distance is larger than the sum of their respective radii. And what happens then is that you are actually dominated by electromagnetic interactions, and your hadronic interactions are completely suppressed. So, well, if we have a charged particle at rest, it radially radiates electric field. When it starts moving, you also have the magnetic field. And then if it starts moving at relativistic velocities, because of your Lorentz contraction, you get like a concentration of your field lines in the direction perpendicular to your direction. And these high intensity field lines are actually equivalent to the emission of real or quasi-real photons. And the amount of photons, so your photon flux, actually depends on the electric charge of your particle. So the larger the electric charge, the larger your photon. Goes with the dependency square. Now your photon virtuality itself is limited by the inverse of the size of your particles, interacting particles, so your beam particles. This is why you have quasi-real photons, and the maximum photon energy of the photon emitted is determined by the minimum distance at which the two particles can have. And if you put this now in numbers, for example, we had proton lead collisions at the LHC at 8.2 TeV. And the maximum energy of the photon in the rest frame of the beam particle emitting the photon is only 28 MeV, which is really, really small, like it's nothing. But then because of this huge boost, the other beam particle sees this photon having an energy of 1 beta electron volt, which is huge. It's 10 to the 15 electron. This is like really amazing. And this is why you can then reach extremely high photon-proton center of mass energies. And because you have such high photon-proton center of mass energy, you get access to this extremely low X-FINE. And in PP, at 13 TeV, you can even go higher to 4.6 TeV. Okay, so I've already showed this table several times. I'm every time still amazed by how huge the energy. So how do we do this experimentally? Because I said for EP, things are actually quite clean and easy if you work with a fixed target. So what we have one beam particle emitting a photon. This photon anti-charm pair, this charm anti-charm pair interacts with the other beam particles at first order the exchange of two gluons, and then the charm anti-charm pair evolve into a J psi, for example. And this J psi is then reconstructed through its decay, mostly into oppositely charged muons. Electron positron is also a possibility that means that there is more Bremsstrahlung radiation because of the low mass of the atom. Now, what you then do is that you detect your two leptons in your detector, and then since it's an exclusive measurement, you then require large regions void of any particle activity, and you try to go as close as possible to the P-line as possible. And that's it. There is no detection of the hadron emitting the photon, and you also have no detection of your scattered particle. There are Raman pods at the LHC, but they detect photons for interactions where what you produce here has a much higher mass, so this is then not adequate for the study at the moment of GP. Okay, so just for you to know, there are Raman pods, but we cannot use them for this type of. So the only thing you have in these two particles and requiring that you don't see any activity in your detector. Your momentum transfer is actually quite well reconstructed just by equating it to the transverse momentum squared of your chip size. So that's not an. Now to try to be exclusive, what you try to have as many detectors as possible. So this is just an example for the LHCb detector, where here you have the range in rapidity. Again, rapidity is approximated in first order with the coverage in polar angle. So you see it has the main detector here. It has some acceptance here, but then here there are holes, here there are holes, and here there are holes. And then for a few years, the LHCb experiment also took data with, in addition, on scintillators on both sides of the main detector up to like plus or minus 115 meters away from the interaction point, which allows you to see if some particles were created or not. But you do have gaps, so it's really not as clean as in fixed targets. Nevertheless, like it's really useful. So imagine we now are interested in studying the proton. Well, then you can do things. You can look at data where you had the collision of a lead ion and a proton. This is really nice because, as I said, the photon flux is proportional to the electric charge square of your beam particle emitting the photon. So if you have a lead ion and a proton, well, it's much more likely that it's your lead ion that will emit the photon and not. So at first order, you know which of the two particles was emitting the photon, and you know which particle you are actually probing. On the other hand, if you look at PP collisions, the positive aspect is that you can go Bjorken, but when you perform your measurement, so you just have a PP collision, you reconstruct your shape side, well, your total cross-section will have a contribution from either the proton going towards your detector, emitting the photon, or the proton moving away from your detector, emitting the photon. Both of these enter in your total cross-section, and you don't know which one was actually emitting the photon. Now, what was done at LHCb is that, so if you have the photon going towards your detector emitting the photon, this corresponds to a photon with very high energy, so a large photon-proton center of mass energy. So this is this part here of the equation. This is the thing you don't know because we have never reached that region before. On the other hand, if it's your proton moving away from your detector emitting the photon, then this corresponds to a lower center of mass energy. And there we have coverage from the HERA collider experiments. So what you do is you use information from the HERA collider experiment, you plug it in here, and then from this you extract this. Yeah, so that's what's done in fact. Now, so once you've done all this, you have extracted your measurement, which is this part here, your photon-proton cross-section that you're interested in, because this is the one that gives you access to your GPDs. The emission of the photons is something you can calculate. There are different Monte Carlo simulations that you can use for this. So then you can actually look at the photon production cross-section for exclusive JFSI as a function of this photon mass energy, or equivalently as a function of Bjorken. And these measurements, since nothing is polarized, you're just measuring cross sections, this is actually sensitive to your GPDH. What you can do is then compare results from ALICE in red and orange, where they perform measurements. There are results from the LHC experiment, where they perform measurements in proton collisions. So you have the low energy solution, which is actually from this extraction from metadata, and then the new region, which are these green open points. And you see we can be down to 10 to the -6. Then you have also the older target experiments here, and then the H1 and 2 collider experiments. And what is really nice in this plot is that even though we use different collision systems in the region of common kinematic coverage, the data really seems to be consistent with one another. So this really hints at the fact that we're actually probing the same underlying physics. That's really beautiful. You can then perform the same measurement by looking at exclusive epsilon production, where you have less data points. This has higher mass, so it's harder to produce. But also there, if you compare with the meta experiment, and the LHC data, well, the data does not, but the different data sets seem to not be incompatible with one another. And the advantage of looking again at epsilon production is that you probe your GPDH at a higher Q-score scale. Now, so I said, but this is just to show it visually. So we have in total 8 leading twist GPDs. There are actually also other GPDs. And I've shown you that, for example, just looking at the whole production and performing a fit of your angular distribution, you get access actually to all of these GPDs. So this is really cool with exclusive whole production in EP collisions. Now with the LHC, we only have access to this one. So it looks a bit sad if you plot it this way. I have, again, the LHC has really this advantage of going down to very low X, and I have to nuance this statement a little bit in the sense that there have been some theoretical studies where you can look, for example, at the production of a photon with a hole or of 2 photons. These are not easy measurements, but this would then give you access to transversity GPD. So these ones here, even though your protons are not polarized. The only thing is, so these processes are likely to work for JLab kinematics. It might be that at the LHC, the cross-section is just really too low. That's still something maybe to look at. And then as for the TMDs, we can use the LHC spin project if it's going to be installed or when it's going to be installed to access the spin-dependent GPDs such as the GPD, again through these ultra-peripheral collisions using the fixed star. Now, we can also look at ultra-peripheral collisions in lead-lead collisions. And so what are we then probing? So we have, this is a beautiful lead ion with inside protons and neutrons with inside their shell. And you have then the other lead ion that emits a photon, and this photon can then probe the other beam ion. What it can do is that it can interact with this beam, this ion or this nucleus as a whole. And then we talk about coherent scattering, and then usually your nucleus does not break up. What can also happen is that the photon interacts with one of the nucleons inside your nucleus, and then we speak about incoherent scattering, and your nucleus actually then usually breaks up. Now, both processes are very interesting. I will start by discussing a coherent production. Now, one of the reasons why this coherent production is interesting is that we might be sensitive to nuclear effects. So we know that if we study PDFs and we compare the PDF from a 3 proton to the PDF of a proton in a nuclear environment, then we see that the ratio is not equal to 1. So here, this is the ratio of the normalized PDF in the nuclear environment compared to the PDF from your free proton, and you see that this ratio is sometimes below or sometimes above 1. And there are different explanations for this different behavior, but we don't understand the origin of this effect. There are some hypotheses, but nothing is patent. Okay, and the other reason why it's interesting to look at coherent scattering is they're not directly related to GPDs, but it's interesting by itself. So we know that at high X, we're dominated by the valence PDFs, and then the lower and lower you go in X, the more and more contributions you have from C quarks, and most of all, the more and more contributions you have from gluons. Now in this picture here, it shows you the PDFs as a function of X, weighted with X. But for the gluons and the C quarks, this is a multiplied by a factor of 0.05. And if for the gluons you remove this factor, you really actually see that you have a huge rise in your gluon distribution. And the idea is that at high X, well, you have your valence quarks, and then the lower and lower in X you go, the more and more gluon splitting you actually see. And the expectation is that at some point, you will have so many gluons, your nucleus will be packed with so many gluons that your gluons will start to recombine. And so this distribution here will not continue rising, but expected that it flattens out. So that's the expectation, but it hasn't been seen experimentally. Now, in order to probe this, you like to use an environment that has many gluons. Because what happens is that you have your photon here impinging on your object, like your nucleon or your nucleus, and let's say your gluons, and your photon will interact with all the gluons that are located at this transverse position. So all the gluons also that are located here. So if you use a nucleus where you have by default much more nucleons, so much more gluons, so you will have interaction at this point here with a whole much more gluons compared to if you would just probe a single nucleus. Yes. So this is why it's useful to look at nuclei if you want to probe saturation. And this coherent scattering is expected to be sensitive to saturation. Now, the drawback though is that when you look at your cross-section as a function of this variable t, which is a measure for the squared momentum transfer to your target, then you see that at very low values of t, your coherent cross-section dominates. But then very fast, actually for larger values of t, your incoherent cross-section dominates. So if you're interested in studying coherent interactions, you really need to suppress this incoherent contribution drastically. And this is experimentally not and the reason, for example, why you would, apart from doing it, why you would like to do this, if you're interested in GPD related physics and you want to, for example, pinpoint down the transverse position or your impact parameter dependent PDFs for different quark flavors, then what you actually need to do is to take the Fourier transform of your GPD, where the transverse component of your momentum transfer, so the perpendicular component of T, is in theory should be integrated from 0 to infinity. Now, infinity is theoretically. In practice, you would cut off at some higher T perp value, and in order to obtain useful information, it seems that you actually should resolve up to your third bump here. You really have to suppress this huge amount. Notice that this here is a logarithmic axis. So where do we stand? So for the EIC, we will perform exclusive measurements on nuclei. So what you see here on the left is from simulations, the coherent contribution. So just the beginning of the third bond, and this is your incoherent contribution. Now, by applying various cuts, one is actually one can reduce this incoherent background down to this contribution here, which means that if you compare the axis, you're able to resolve the first dip here, but this is not yet, the second dip cannot yet be resolved. So we don't manage to suppress sufficient. Just for completeness, I also show you how well we can resolve different bands. So this is work in progress. So things will change in the future. So, but you see that using the available information, we can maybe resolve like the first and second one, but then it becomes a bit more complex. But there is hope because there are new methods on the way to maybe improve it and actually obtain the red curve instruction. But this is just this is work in progress. It's to these are perspectives, but it's not yet final. Now for the LHC, the situation is not better. There they also only can resolve the first peak. So if they look at coherent scattering, it's only this first peak that you. And here you see a measurement for the photo production cross-section on LED for JPSI from the Hulse experiment. And so these are the data points. Here you see the model where you have 0 nuclear effects. You see that this model does not disrupt. Then you have one model where you have this shadowing effect or nuclear effect that is similar to what is happening here. There's nuclear shadowing. And then there is another model where they do not introduce nuclear shadowing, but they include the effect of saturation. And you see that actually both models do describe the data. So at the moment, the effect that we see between no effect at all, which is the group of an effect and some effect, can be nuclear shadowing or saturation. Now, if you remember in PP collisions, I said we have a problem because we don't know which of the beam particles is emitting the photon. Here, at mid rapidity, rapidity close to 0, you don't have this problem, so you can actually extract the photo production cross-section. But we don't have so much time. But in other regions of rapidity, you don't have this luxury. So we are always in the situation that you have either a contribution from the scenario where the lead ion moving away from your detector is in. So then you're in the situation of small photon-proton center mass energy, or you have a contribution where your photon moving towards your detector. Your ion moving towards your detector is emitting the photon, and then you're at large photon ion center of mass. So you always have two contributions. And each of these contributions is weighted with the photon flux, so yeah, from your other beam particle. However, this photon flux has some dependence on the energy of your photon and on how close your beam particles are. So we know that if your beam particles are interacting far away from each other, then the contribution if your beam particles are moving away interacting far from each other, then you will have a smaller photon flux of photons with high energy. On the other hand, if they're close to each other, you will have a larger contribution from photons with large energy. So by playing with how close your beam particles interact, you will have less or more high energy photons in it. And when we look at the interaction of two lead ions, so this is one lead ion, this is another lead ion, one of the two is the photon emitter, and the other one will then be probed, and we will access his nuclear GP. So this is the process here that we know, that we are interested in. But in addition, these two ions can exchange more photons and excite each other. And once they're excited, they need to go back to their ground state. And they do that by emitting neutrons. So the closer the beam particles, the more likely they will excite each other and the more neutrons you expect. But then you also know that you will have a larger contribution here from high energetic photons. So if we're able to detect our neutrons, we actually have a measure of how close your beam particles were into. And this was done, for example, by the CMS experiment. So here you have, so the CMS experiment is like a central detector with here the interaction point. So here you have their central barrel. And then far away, up to 140 meters from each side, they also have 0-degree calorimeters very close to the beam line where they can detect neutrons. So what did they do? They said exclusive J-psi product for the two muons were reconstructed in the central detector. And then they took measurements subdivided in 3 configurations. So they classified events where they didn't see any neutrons in either of the 2 0-degree calorimeters. So then normally on average, your particles were quite far away from each other. They had a category of events where one of the 2 0-degree calorimeters saw neutrons, but the other one not. So then you know your particles are already a bit closer. And then the last category was when both CDCs saw neutrons. So then you know they're extremely close. This vibrated, so it will not last long. Okay, so you have your 3 different measurements, right, for the 3 categories. Each time you have a different photon flux. Well, depending on the energy of your particles, you will have different photon flux for the low energy configuration and a different photon flux for the high energy configuration because they were far away, less far away, and closer to each other. However, your actual photo production cross-section for exclusive J-psi does not change from one category to the other. That never changes. You just have photon of a certain energy interacting and creating a J-psi. This cross-section is. So you measure this flux you can determine from Monte Carlo simulations, for example, Starlight. And this one is constant. So you actually have an over-constrained system, and knowing these, you have only 2 unknowns, namely the 2 photo production cross sections at low and at high energy, and this you can then extract without any ambiguity and cleanly from your 3 measurements. And this has been done by the CMS experiment, so where they looked at the exclusive photo production on LED as a function of the photon nucleon center mass energy, and what they saw is that at low values, the cross-section was really rising a lot, which would actually correspond to a rise of your gluon distributions. And then at larger energies, this cross-section seems to flatten out quite a lot, which might correspond to the fact that your gluon distribution is flattening out. This is just like some interpretation, so be careful, but so this is what is seen, and this is really clean and extremely nice. And then a similar measurement has been performed by the Alice experiment, where they actually reached higher energies. Okay, now we can also look at incoherent production, where your photon interacts with one of the nucleons inside the nucleus. So, written out in terms of averages and variances. So we have our total cross-section with both together. It's just like the average of the cross-sections. Then we have the coherent contribution, where you take the average over all possible target configurations squared. And then you have the incoherent contribution, where you make sure that you have a final state that is different from your initial state. And you write the expectation value squared you sum over the different initial and final states for expectation value. You write this out in terms of conjugates. Write it out according to this expression, and this expression is actually just your total cross section minus your and this actually as the expression of variance. So what this incoherent cross section is meaning is actually as probing is the variances of your distribution. So you have your coherent cross section, which is related to your GPDs and which probes actually the average position of your gluons inside nucleus. And then the incoherent one is sensitive to event by event fluctuations of your distribution. So here you see four different ranges in rapidity, which corresponds to different ranges in X-Björken. You see the Y and X components of your transverse position. And so the idea is by looking at these incoherent interactions, you will see the fluctuation and not just the average distribution. So you will see differences if you're closer or further away from the center. So that's extremely nice. So this is peripherally related to GPD. And this measurement has been performed by the Hulse experiment in proton lead and in lead-lead collisions. And I did mention it because I thought I was not going to have enough time. But so the way they isolate incoherent from coherent production is by looking at transverse momentum of your produced shape size. So you have, if you have, okay, so you have, yes, here. Okay, doesn't matter, like forget the electron. You have your photon and your beam particle, and they interact and they produce a shape size. So it's an exclusive process. So the transverse momentum created here must be equal but opposite to the transverse momentum created here. If in the initial state you don't have any transverse momentum. Okay? Yes? Okay, so you know that if this shape size got a very big kick, it means that your final state or your interacting beam particle also got a really big kick, just by compensation. Now, the bigger the kick, the more likely your beam particle will break up. Yes, so the more likely you will actually probe incoherent interaction. So that's what they used here. So you see here, this is the most beautiful one, I think. So this here, the transverse momentum distribution of your shape psi, and here in green, you see nicely the coherent peak, and then you see that this goes only to very small values in PT, and then for larger values, you see contributions from different types of incoherent processes. So they just isolate this by making cut on the transverse momentum and correcting for background contribution. So when you do this, you can then plot the photo production cross section. So this was in lead. So we were actually looking at the of a proton and the following production of a shape psi. And here you see the results from Hulse in pink or magenta, and the results from the H1 experiment at Hera, because they also looked there at dissociative shape psi production, and the data points seem compatible. And then here you have for the lead production, the distribution as a function, the cross section, sorry, as a function of the Mandelbrot variable T, so the photo production cross section. These are the data points. And then you have two models. So the band is one model where you have a nuclear effect, and then the dashed lines are another model. And in one case, they do not include these fluctuations, and in the other case, they do include fluctuations. Now, the models and the data points, the normalization is off, but if you would just concentrate on the shape, you see that for these data points here, this shape much closer to the T dependence compared to this one. And this one here corresponds to the inclusion of event by event fluctuations. And you can say the same for the other model. So it seems that it is indeed important to take into account this fluctuation. Okay, so in a summary, we'll address the different types of in structure related variables and observables and measurements. So it all started with the MC effect, performing inclusive EP measurements where they show an extremely small contribution to the spin of the quarks to the spin of the nucleon. Then new experiments were created to check the result and make more precise measurements. And now we see that we have a quark spin contribution of around 30%. If you look at the Q-square evolution of the inclusive measurements, and even more importantly, if you include data from the PP collider at RIC, which was polarized, you see that for values above 0.05 in X-Bjorken, we have indeed positive and non-negligible contribution from the gluon helicities to the spin of nucleon. And if we want to identify the difference or separate the different quark flavor spin contributions, we can look at same inclusive scattering, where we detect also one of the produced hadrons. Or in PP collisions, we can look at W production with one of the beam hadrons polarized. And there we saw, for example, that we have an asymmetry in the U bar minus P bar helicity distribution. Using these same inclusive measurements, we can also actually access whole series of TMD PDFs. For example, we looked at the Sievers distribution function, where we looked at the correlation between transverse momentum of your proton and the transverse spin of your nucleon. And though it doesn't give you direct information about the orbital angular momentum of your quarks, it does mean that there is a non-zero orbital angular momentum. It can still mean that the sum over all contributions of the angular momentum can be zero, but it shows you there is angular momentum. If you then try to really pinpoint down the quark and gluon orbital angular momentum, in theory, you can look at EPDs, though in practice, well, it's not so easy. So you can study GPDs in EP collisions and at the LHC. So for the future, we can expect really nice results from Jefferson Lab at high X and DIC down to 10 to the -4. And for the LHC, so with the upgrade towards high luminosity, meaning more and more interactions, PP collisions will not be providing any information anymore, because there are too many multiple interactions at the same time. So it's really difficult to isolate exclusive events. But in proton LED and in LED, we should be able to do so. So that was all. I don't know if there are any questions.
Are there any questions?
This might be a dumb question, but so you mentioned that when you get like a J psi produced, then you detect that it's a J psi by looking at the muons it decays into. Why can't you just like detect the J psi? Is it because it has such a short lifetime?
Exactly. So it just decays immediately. And the way you can, I rushed a bit, but the way you can then reconstruct the J psi is just by looking at a bit here. So you can just look at invariant mass of your two muons. And so this is just a continuum. This would be your beta head. And then you first see the first J psi peak, and then second peak is this psi 2s. But it just decays immediately. So you have no way we could.
All right, thank you.
You're welcome.
Hello, at some point you had mentioned that the double DVCS gave you access to that variable X. I was wondering if you can elaborate on how like specifically the two virtual photons allows you to access that variable X as opposed to just the one.
No, I can't. So I think it's just when you write this out here, you get this convolution. But I don't know, I don't remember, so I cannot write it down for you. So, but you have, if this would be for your GPDs, you would have here like X minus psi, which is your hard interaction times your GPD. And for double virtual Compton scattering, you can rewrite this and it falls out, but I don't know, I'm sorry. I read it in the past, but I forgot the expression.
Any other questions? Okay, then let's thank Charlotte again